Most people think the Mariana Trench is the deepest place on Earth, the final boundary, the absolute bottom. But even that isn't where the ocean ends. Beneath the trench itself lies a place so deep that our instruments struggle to describe it accurately. A place where pressure deforms steel, darkness erases direction, and human presence is reduced to brief, fragile visits. It's called the Challenger Deep. We've lowered machines into it. We've sent humans down. Briefly, we've taken measurements, samples, and images. And still, much of what we record comes back incomplete. Readings don't always agree. Observations conflict. And long stretches of the seafloor remain unseen, untouched, and unverified. There are no monsters in this story, no legends to chase. Just a simple, unsettling reality. We've been there, and we still don't fully understand what we saw. What makes this place disturbing isn't what's down there. It's how little we can confirm. In the early 1800s, the deep ocean wasn't mysterious. It was dismissed. Most scientists of the time believed that life simply couldn't exist beyond a certain depth. The pressure was thought to be too great, the darkness too complete. Some even argued the seafloor was permanently frozen, locked beneath layers of near-solid water. Others imagined something different. Not frozen, but empty. A vast, flat plain stretching endlessly beneath the waves. Silent, featureless, dead. These ideas weren't careless guesses. They were reasonable conclusions based on the limits of the era. No one had seen deeper than a few thousand feet. No one had the tools to measure what lay below. And without evidence, the ocean became a place defined by assumption. Two major schools of thought emerged. Some believed increasing pressure alone made life impossible. Others argued that without sunlight, the deep sea could never support anything living. Both sides agreed on one thing: whatever lay far below the surface wasn't worth looking for. The ocean wasn't considered hostile. It was considered irrelevant. At the time, science moved cautiously. Explorers focused on coastlines, shipping lanes, and shallow waters where trade and survival mattered. The abyss didn't offer resources, answers, or incentives, at least none anyone could measure. And so the deep ocean faded into the background. Not feared, not protected, simply ignored. But that ignorance wasn't the result of arrogance. It was the result of limitation. Without sonar, without pressure-resistant instruments, without reliable ways to retrieve samples, there was no practical method to challenge those assumptions. The ocean wasn't hiding anything from humanity. We just couldn't reach it. And for decades, that boundary between what could be known and what lay below remained firmly in place, waiting for someone willing to lower a line far enough to prove everyone wrong. In December of 1872, a British naval ship quietly left England with a mission no one had attempted before. Its name was HMS Challenger, and unlike most voyages of the era, this one wasn't about territory, trade, or war. It was about depth. The ship's crew included scientists, engineers, and sailors, tasked with answering a question most people had already dismissed. What actually lies beneath the open ocean? Without sonar or electronic instruments, their method was brutally simple: a long rope, heavy lead weights, and patience. At regular intervals, the crew stopped the ship, lowered the weighted line over the side, and waited, sometimes for minutes, sometimes for hours. The process was slow, exhausting, and repetitive. Sailors hauled hundreds of pounds of wet rope back onto the deck by hand, inch by inch, marking depth as they went. Most of the time, the line behaved as expected. It dropped, slowed, then went slack. Another measurement logged, another routine stop. But on one sounding in the Pacific Ocean, southwest of a remote island chain, something changed. The rope kept falling. Minutes passed. Then more time. The weight didn't slow. It didn't touch bottom. It just continued downward, disappearing into water that grew darker and colder by the second. Crew members watched the marked rope slide endlessly through their hands. More line was paid out, then more, and still nothing. Eventually, after an uncomfortably long wait, the rope finally went slack. When the measurement was calculated, the results stunned everyone on board. The depth was over 5 miles. This single reading challenged nearly everything scientists believed about the ocean floor. It suggested the seafloor wasn't flat, it wasn't shallow, and it certainly wasn't uniform. When news of the expedition's findings reached the scientific community, maps were redrawn. Long-held assumptions collapsed. The ocean was no longer a simple basin. It was structured. It was extreme. And somewhere beneath those Pacific waters, the crew of HMS Challenger had just revealed the edge of something far deeper than anyone had imagined. They had discovered the trench that would later bear its name. For decades after the original HMS Challenger's expedition, the deepest parts of the ocean remained mostly theoretical. Scientists knew trenches existed, but how deep they truly went was still an open question. Rope soundings had limits, human patience had limits, and the ocean had both time and depth on its side. That began to change in the early 1950s. In 1951, a new British survey vessel, HMS Challenger I-2, returned to the same region of the Pacific. This time, the goal wasn't exploration for its own sake, it was precision. Instead of relying solely on rope, the crew used echo sounding, a technique that sent sound pulses downward into the water. When those pulses struck the seafloor, they bounced back. By measuring how long the signal took to return, scientists could calculate depth with far greater accuracy. The concept was simple. The results were not. As the survey continued, the readings revealed something unexpected. The trench identified decades earlier wasn't uniform. It wasn't a single continuous slope. In one area, the ocean floor dropped again, not gradually, not evenly. It plunged into a deeper pocket hidden within the trench itself. Repeated measurements confirmed it. This wasn't an error or a glitch. The echo returns were consistent, showing a narrow region that descended far beyond the surrounding seafloor. The depth was measured in miles, not thousands of feet. At this point, the Mariana Trench was no longer the deepest known feature of the ocean. Within it existed something even more extreme, a point so deep it stood apart from everything around it. This location would become known as the Challenger Deep. To put the scale in perspective, this wasn't just a deeper part of an already deep trench. It was a geological anomaly, a bottom within a bottom, a place where the Earth's crust folded inward farther than anywhere else on the planet. And for the first time, humanity had identified not just the deepest trench, but the deepest point on Earth itself. The ocean isn't a single environment, it's layered. As you descend from the surface, conditions change gradually at first, then relentlessly. Scientists divide the ocean into zones, each defined by light, pressure, and what can survive there. The uppermost layer is the sunlight zone. This is the ocean most people recognize: waves, fish, coral, and warmth. Sunlight penetrates easily here, and life is abundant. Below that lies the twilight zone. Light fades quickly, colors disappear, and shadows dominate. Vision becomes unreliable. Creatures here adapt with larger eyes, or bioluminescence, producing their own light in the dark. Then comes the midnight zone. At this depth, sunlight is completely gone. No matter how clear the water is above, nothing reaches this far down. The temperature drops. The pressure increases dramatically. Any sense of orientation begins to disappear. Below the midnight zone is the abyss. The seafloor here is vast and cold, stretched across enormous distances. Temperatures hover near freezing. The pressure is crushing, and movement becomes slow, deliberate, and rare. But even this is not the bottom. Beneath the abyss lies the Hadal zone, named after Hades, the underworld. This zone exists only inside deep ocean trenches. It begins nearly 4 miles below the surface and extends to the deepest known points on Earth. This is where the Challenger Deep is located. The scale is difficult to grasp. If Mount Everest were placed at the bottom of the Challenger Deep, its peak would still sit more than a mile beneath the ocean's surface. The Grand Canyon, often described as incomprehensibly deep, is more than 5 times shallower by comparison. Here, pressure increases to levels that erase mistakes. Over 1,000 times greater than at sea level, it deforms metal, shatters glass, and compresses unprotected bodies instantly. Darkness is absolute. There is no horizon, no up or down without instruments, just cold, crushing water pressing in from every direction. This is not a place humans were ever meant to occupy. And yet, despite everything working against it, this is the environment we eventually chose to enter, not because it welcomed us, but because it existed. Pressure is the defining force of the deep ocean. Every 10 meters you descend, the weight of the water above you increases. It stacks relentlessly. By the time you reach the depths of the Challenger Deep, there are nearly 7 miles of ocean pressing downward. The result is pressure more than 1,000 times greater than what we experience at sea level. It's difficult to visualize, but one comparison makes it clear. Imagine the weight of dozens of fully loaded commercial airplanes concentrated onto the surface of your body, not pushing from one direction, but from every direction at once. This pressure doesn't tear things apart. It crushes them inward. Most conventional submarines are designed to operate a few thousand feet below the surface. Beyond that, their hulls deform, windows fracture, structural seams fail without warning. At extreme depths, failure isn't gradual, it's instantaneous. That's why deep-diving submersibles rely on thick spherical pressure hulls. The shape distributes force evenly, minimizing weak points. Even then, materials must be chosen carefully. Steel alone isn't enough. Glass becomes a liability. Any imperfection can become catastrophic. Technology that works flawlessly near the surface often fails here without explanation. Electronics short, seals compress, mechanical parts lock or snap. Sensors give conflicting readings or stop responding altogether. And through all of this, darkness never relents. Sunlight disappears miles above. Artificial lights reveal only narrow cones of visibility, surrounded by endless black. Beyond their reach, nothing reflects. Nothing moves, nothing can be confirmed. In this environment, mistakes don't accumulate, they end things. The deep ocean offers no margin for error, no recovery time, no second chances. And yet, despite the crushing pressure, the freezing temperatures, and the absolute darkness, life exists. For a long time, pressure was thought to be an absolute barrier, a hard limit beyond which life simply couldn't function. The depths of the ocean were assumed to be sterile, crushed into emptiness by their own weight. That assumption was wrong. In recent decades, explorers have documented life thriving far deeper than anyone once believed possible. Not large, not fast, but remarkably well adapted. One of the most notable examples is the Mariana snailfish. These small pale fish have been observed at depths exceeding 27,000 feet, making them the deepest living fish ever recorded. They don't survive by resisting pressure. They survive by yielding to it. Their bodies are soft and flexible, with minimal bone density. Instead of rigid skeletons, they rely on cartilage and gelatinous tissue that doesn't collapse under extreme force. Unlike shallow water fish, they don't have swim bladders, gas-filled organs that would compress and fail at depth. Their buoyancy comes from their structure itself. Movement is slow, deliberate, efficient. Vision plays only a minor role in their survival. In the darkness of the deep, sight is unreliable. Instead, these fish hunt by sensing movement, opening their mouths suddenly to draw in small crustaceans with suction rather than pursuit. And then, there are the sightings that don't fit neatly into categories. Rare footage has captured glimpses of deep-sea squid at extreme depths, elongated forms drifting at the edge of visibility. These animals are seen so infrequently that scientists know very little about how they live, reproduce, or even how many exist. They appear briefly, then vanish. The deep ocean doesn't offer clear answers. It offers moments. Every observation comes with a limitation. Cameras illuminate only a few meters at a time. Sensors record what passes directly in front of them. Everything else remains untouched, undocumented, and unknown. What we've learned so far suggests something important. Life doesn't conquer the deep. It adapts quietly to it. And even now, with our most advanced technology, we only see what our lights reach. For all the data gathered by machines, there came a moment when scientists wanted something else. Direct observation. Human eyes at the deepest point on Earth. That moment arrived in 1960. The vehicle designed for the task was called Trieste. It didn't resemble a traditional submarine. Instead, it was built around a simple principle: survive pressure by avoiding resistance. Its main float was filled with gasoline, not for fuel, but because gasoline is less dense than water and nearly incompressible under extreme pressure. This allowed the vessel to remain buoyant without collapsing. Beneath the float hung a small, spherical steel cabin, just large enough for 2 people. The walls were over 5 inches thick. Inside were Swiss oceanographer Jacques Picard and U.S. Navy Lieutenant Don Walsh. The descent took nearly 5 hours. Within minutes, sunlight vanished. Temperature dropped steadily. The only sense of movement came from instruments and the slow ticking of time. Outside the small viewport, there was nothing to see. At around 30,000 feet, a sharp cracking sound echoed through the cabin. The outer acrylic window had fractured. For a moment, neither man knew whether the hull had been compromised. There was no way to inspect the damage, no backup vehicle, no rescue plan. The only thing separating them from instant collapse was a second internal pain that, somehow, held. Against expectation, they continued. Eventually, Trieste touched the seafloor. Jacques Picard and Don Walsh became the first humans to reach the Challenger deep. They remained there for roughly 20 minutes. During that time, they reported seeing movement outside the window, a flat shape along the sediment, and what appeared to be shrimp-like creatures drifting past. But the view was limited. Sediment was disturbed by the landing. Visibility was poor. Years later, some scientists questioned those observations. Fish, they argued, should not survive at that depth. What was seen may have been something else entirely. Perhaps a sea cucumber, distorted by light and motion. The uncertainty remains. What matters is this: two humans reached the deepest point on Earth, stayed only briefly, and returned with more questions than answers. Even at the bottom of the ocean, clarity was not guaranteed. After Trieste, it became clear that sending humans to the deepest parts of the ocean was neither practical nor sustainable. The risks were enormous, the time at depth was minimal, and every descent pushed the limits of survival. So exploration changed. Instead of people, scientists sent machines. In the mid-1990s, Japan deployed a remotely operated vehicle called Kaiko. Unlike earlier submersibles, Kaiko wasn't built for brief visits. It was designed to return again and again, descending into the Challenger deep without human lives at stake. Tethered to a surface vessel by a long cable, Kaiko carried cameras, sampling tools, and sensors capable of functioning under extreme pressure. On multiple dives between 1995 and 1998, it reached the ocean floor, becoming the first vehicle to do so repeatedly. For the first time, researchers were able to collect sediment directly from the deepest point on Earth. Video footage revealed small but unmistakable signs of life: sea cucumbers, amphipods, and worm-like creatures moving slowly across the seabed. This was no longer theory. Life existed there. But even with this technological leap, the limitations were obvious. The vehicle's lights illuminated only a narrow cone in the darkness. Beyond that, the seafloor disappeared into blackness. Objects appeared briefly, then faded from view. The tether restricted movement. The pressure still threatened mechanical failure. And every dive required careful planning and constant monitoring from the surface. In 2003, Kaiko was lost during a typhoon, severed from its support ship, and swallowed by the same depths it had helped explore. The data it returned was invaluable, but the picture it painted was incomplete. Machines could reach the bottom, they could confirm life, they could collect samples, but even with repeated visits, most of the Challenger deep remained unseen. The deepest place on Earth had allowed us in, only partially. In 2012, the next person to reach the Challenger deep wasn't a career oceanographer or a military pilot. It was James Cameron. While best known as a filmmaker, Cameron had spent decades immersed in deep-sea exploration. He had logged dozens of dives to the wreck of the Titanic, studied submersible design, and worked closely with engineers to develop new deep-diving technology. This time, he wasn't a passenger. He piloted the deep-sea Challenger alone. Unlike earlier submersibles, the vehicle was built as a scientific platform. Its narrow, vertical design reduced stress from pressure. Buoyancy came from syntactic foam, a material made of microscopic hollow spheres capable of resisting compression at extreme depths. The pilot's compartment was a reinforced steel sphere, barely large enough for one person. The walls were built to withstand pressures exceeding 16,000 pounds per square inch. The descent took just over 2 hours. When Cameron reached the bottom, he stayed. For nearly 3 hours, he explored the seafloor, maneuvering carefully through sediment while capturing high-resolution footage and collecting samples with a robotic arm. This was the longest and most detailed human visit to the Challenger deep up to that point. When he returned to the surface, Cameron described the landscape as stark and lunar, flat, empty, almost lifeless, but the samples told a different story. Scientists examining the material he retrieved found small crustaceans and microorganisms adapted to extreme pressure. More importantly, they identified unique chemical compounds in these organisms, molecules that showed potential for medical research, including possible applications in understanding neurodegenerative diseases. The environment looked barren. It wasn't. Life existed quietly, hidden in sediment and darkness, operating on timescales and rules completely unlike those near the surface. Cameron's dive proved something crucial. Even when the deepest place on Earth appears empty, it isn't. It simply exists beyond the limits of casual observation. By the late 2010s, reaching the Challenger Deep was no longer a once-in-a-lifetime achievement. It became repeatable. In 2019, explorer and former naval officer Victor Vescovo descended to the bottom of the Challenger Deep aboard the DSV Limiting Factor, a compact, pressure-resistant submersible designed for repeated extreme dives. Unlike earlier vehicles, it was built not just to survive the depth, but to return again and again. And it did. Vescovo completed multiple dives to the deepest point on Earth in a matter of days. Over the following years, he would return more than a dozen times, spending extended periods exploring areas never before revisited. What he found was unexpected. Alongside the familiar sediment and sparse deep-sea life, there were unmistakable signs of human presence. A plastic bag, candy wrappers, synthetic debris resting quietly on the seafloor nearly 7 miles beneath the surface. There was no dramatic reaction, no alarm, just confirmation. Human pollution had reached the deepest place on Earth. Later analysis revealed something even more troubling: microplastics. Tiny fragments formed as larger plastics break down were present in sediment samples from the Hadal zone. These particles sink slowly through the water column, accumulating over time in the deepest regions of the ocean. This wasn't an accident or a single event. It was the end of a long process. The Challenger Deep had remained untouched for millions of years, and within decades of industrial plastic production, it carried our residue. No ecosystem is isolated, no depth is protected by distance alone. The deepest point on the planet didn't reject us, it recorded us. And what it recorded wasn't exploration or discovery or progress. It was evidence. Where information is limited, theories tend to grow. The Challenger Deep is remote, inaccessible, and rarely visited. Very few people have seen it directly. Even fewer have spent time there. And for long stretches, exploration goes quiet. That silence creates space. Some theories suggest the depth and isolation make the Challenger Deep an ideal location for secret government installations. The logic is simple. No civilians can reach it, pressure prevents surveillance, and failure would leave no witnesses. Others go further. They argue that undiscovered marine species, perhaps survivors of ancient lineages, may inhabit regions we've never illuminated. The idea isn't entirely unreasonable. More than 80% of the ocean remains unexplored, and new species are discovered regularly in far shallower waters. Then there's the sound. In 1997, underwater microphones operated by NOAA recorded an extremely loud, low-frequency noise in the Pacific Ocean. It was detected thousands of kilometers apart and became known as the bloop. Some speculated it came from a massive living organism, something larger than any known animal. For a time, the mystery remained unresolved, but when examined carefully, each theory begins to weaken. Building and maintaining any facility at such depth would require constant access, power, and structural integrity under crushing pressure. Even today's most advanced submersibles can only remain at the bottom for limited periods. As for hidden megafauna, the environment itself imposes constraints. Food availability is scarce. Temperatures are near freezing. Large, energy-demanding predators would struggle to survive there undetected. The bloop, once studied in greater detail, matched the acoustic signature of icequakes, the cracking and movement of large ice masses. When played at normal speed, the sound loses its biological character entirely. And yet, the ocean doesn't offer total certainty. We don't monitor every trench continuously. We don't see beyond our instrument's range. And we don't fully understand how life adapts under extreme conditions. Theories thrive not because the answers are hidden, but because they're incomplete. And in places like the Challenger Deep, incompleteness is the default. At first glance, it seems counterintuitive. Why would a space agency care about the deepest parts of the ocean? The answer lies in extremes. The deep sea is one of the harshest environments on Earth. Crushing pressure, freezing temperatures, total darkness, limited resources, isolation. These are conditions that mirror those found beyond our planet. For NASA, the ocean isn't a distraction from space exploration. It's a rehearsal. Studying life in the deep ocean helps scientists understand how organisms survive in environments once thought uninhabitable. Microbes, crustaceans, and soft-bodied animals thrive under conditions that would destroy most life on the surface. Their adaptations offer clues about how life might exist elsewhere in the universe. One of the most compelling comparisons is Jupiter's moon Europa. Beneath its frozen surface lies a vast saltwater ocean, possibly containing more water than all of Earth's oceans combined. There is no sunlight there. Pressure is immense, temperatures are extreme. And yet, if life can survive in Earth's deepest trenches, it may also exist beneath Europa's ice. NASA studies Earth's oceans to learn what signs of life to look for, and how to recognize them when direct observation is limited. The deep sea also serves as a testing ground for human endurance and technology. Submersibles, life support systems, communication delays, confined spaces. These challenges closely resemble those faced during long-duration space missions. Before sending humans to distant worlds, agencies need environments where failure is possible, lessons are immediate, and survival depends on preparation rather than luck. The ocean provides that. What began as an attempt to understand our own planet has become a bridge to understanding others. The Challenger. Deep isn't just the lowest point on Earth. It's a reminder that exploration doesn't always point outward. Sometimes, the path to the stars begins by looking down. For most of human history, the deepest parts of the ocean existed only as speculation. They were imagined, debated, and dismissed without evidence. That is no longer the case. We've reached the deepest point on Earth. We've measured it, we've mapped it, we've sent humans and machines into its darkness. And still, it refuses to feel understood. Every expedition returned with fragments, readings, samples, brief observations, but never a complete picture. Instruments fail. Visibility vanishes. Interpretations change. Even first-hand accounts are questioned years later. The Challenger Deep is not frightening because it's unexplored. It's unsettling because it has been explored. Despite all our technology, all our preparation, and all our effort, the deepest place on Earth remains partially inaccessible. Not sealed, not hidden, just beyond full comprehension. That should give us pause. If a place on our own planet, one we can physically reach, still resists clarity, then uncertainty isn't an exception. It's a constant, the challenger. Deep doesn't scare us because it's unknown. It scares us because we've seen it. And the answers didn't come back with us. And maybe that's the point. Some environments don't offer conclusions. They offer reminders. That knowledge has limits. That exploration doesn't guarantee understanding. And that silence isn't always empty. If you have a theory, share it below. Some places don't give clear answers.